Okay. So we have a battery, an inductor, and a capacitor in the switch. And the values are given here. And we start out with the switch in position A to fully charge the capacitor. Then we flip the switch to position B. And we know that the current and the charge are going to be oscillating in this LC circuit. Both of them, the charge on the capacitor and the current in the circuit, these are going to be described by these sine and cosine functions. So the first thing we want to know is the frequency of this oscillation. So we start out by calculating the angular frequency, because we know for an LC circuit, omega squared is 1 over LC. So let's do that. So L is 42 millihenries. Mill is 10 to the minus 3. So we can put that on top. And then we have 65 microfarads. Micro is 10 to the minus 6. And now we have to check the units here. A volt times a second is a Henry times an amp. And a coulomb, let's do this here. Our units are going to be 1 over a Henry times a farad. So a volt times a second, here a Henry times an amp is a volt times a second. We also know a coulomb is equal to a farad times a volt. And an amp is a coulomb per second. So an amp times a second is a coulomb. So I can't really fit all these conversion factors up here, but let's just check. So Henry's cancels, farads, amps, coulombs, volts, and what we get are inverse seconds squared, which is what we should get. When we take the square root, we'll get inverse seconds. So it'll actually be radians per second. So I'm just going to do this. Say a Henry times a farad is equal to a second squared. So, that is true. Yeah, so now let's find this numerically. This is going to be a rather large number. Things are going to be bouncing around pretty quickly in this circuit. Let's see what we get. Okay, so we have 1,000 divided by 42. Okay, let's just do this. Let's do 42 times 65. That's 2730. So we have 10 to the 9th. So you can say that's 10,000. So 1,000 obviously wouldn't be big enough to get this in scientific notation. Actually, I'm going to do this. So this is 10 to the 5th over 2730, because this exponent's a little too high, of course. We'll get a number greater than 10. But when we take the square root, taking the square root of 10 to the 4th will just give us 100. So let's do 10 to the 5th over 10 to the, so it's divided by 2730. That's 36.63. So the square root is 6.05. And so omega, then we multiply by 100. That is 605 radians per second. And so the frequency is 2 pi over omega. So let's do that now. This is 0.01 hertz. Right. What did I do here? Yeah, never mind that. But that was rather slow. Things should be bouncing around very quickly. Frequency is omega over 2 pi. So let's try that again. So we have 605 divided by 2 pi. And again, if you're doing this on a calculator, you want to be careful. You don't just want to say 605 divided by 2 pi and hit enter because of the order of operations. So it would divide by 2 and then multiply by pi, which would, of course, be wrong. So anyways, that's the frequency. So remember, a full cycle is a charge starting on the capacitor, it flips polarity and then flips again to get back where it started. It would do that about 96 times every second. So this is going around the energy is going to be flipping back and forth very rapidly. We could find the total energy in the circuit if we wanted to. Yeah, we know for a capacitor, let me write this down. We don't need that time constant right now. Yeah, Q is equal to CV for a capacitor in general. So the maximum charge is going to be C epsilon. So like whatever the voltage across capacitor is, that depends on the charge. Well, we know the maximum voltage is just going to be the EMF of the battery. So we can find the maximum charge on the capacitor. That would be 65 microfarads. Leave it actually. Times 9 volts. And a coulomb is equal to a farad times a volt. And so we can just cancel out the farad and the volt. And so our units are going to be microcoulombs, which might be reasonable. So yeah, what we're getting is 585 microcoulombs, or 0.585 millicoulombs, but either one would be appropriate here, or you could always do scientific notation. And so the maximum energy would occur when discharge is on the capacitor. So let's find the total energy. So again, when all the charge is on the capacitor, there's zero current. So the total energy would be Q max squared over 2C. So again, it's not going to be too much energy. So micro is 10 to the minus 6. And then 2C, that would be 130 microfarads. So micro, 10 to the minus 6, or 10 to the plus 6 on top. And one of those will cancel out. So let's see. We want to get joules out of this. So we have to get rid of farads for sure. Let's see. Coulomb is a farad times a volt. And a joule is equal to a Newton times a meter. Something is still missing here. I'm trying to think what conversion factors we need. Oh wait, this might work actually. A joule is equal to a coulomb times a volt. Yeah, that actually works. So let's just, I'll erase it, but here we have coulomb squared, farads, volts, and joules. On bottom, we have a farad, 2 coulombs here, and a volt. So everything cancels out, we're left with joules. So let's see how much energy here. We'll clean this up a little bit. We have 585 squared. Now, this is 10 to the 6 twice. So let's cancel one of them out here. So let's do this. Say 10 to the 6 microjoules in 1 joule. And so we can then cancel this out as well. So we have 585 squared divided by 130. Let's see. Maybe nanojoules would have been, all right, sorry, millijoules might have been better. Let's do that. 10 to the 3rd millijoules in 1 joule. So this is about 2.63 millijoules. That's what would be stored in this circuit. It's just going back and forth between electric and magnetic fields. Okay, so any questions on this LC circuit? Okay, so let's look at a more realistic case, an RLC circuit next. So I'm going to stop recording this one.